last time. So I want to finish this week the course. So two things left to do. One is the to complete the discussion about the continuum beta function and continuum calculations and the exact RG. Okay. So and then I'll talk a little bit about the Polchinski's argument about renormalizability using the exact RG. So I should be done this week.
So you want to mention Polchinski's equation?
Yeah. So that I'm going to do today. Right. That's the exact RG. So let me complete the discussion last time. So if you remember, what we were doing was getting the continuum beta functions starting from a recursion relation obtained, say, on the lattice, which could. So we started out, I'll just remind you what we did. So we started out writing equations like this. So this is just a summary. So I won't do everything. So we wrote down recursion relations like this. Where I took a sample example where there's one relevant coupling mu, one irrelevant coupling W, and one marginal coupling G. So this is the starting point, and remember the crucial point was that here there's a factor of 4, so this coupling becomes bigger with the recursion, this coupling becomes smaller, this remains the same, the leading order, and these are the nonlinear corrections, and we are assuming that these are small. So we solved it iteratively, and we found that the technique to do that, well, we found that this is easy because if you start with some non-zero value for W, the effect of that doesn't propagate very far because of these factors of 1 by 4. So they have a small effect. Now superficially this seems to give a trouble because it grows, but the solution to that was to, instead of fixing the initial value, you fix the final value. So with respect to the final value, mu L is much smaller than the final value. So you're able to rewrite this as an equation where again there are negative powers of 4. So the effect of the relevant coupling is also damped in the recursion. The one that gave trouble was this one because there's no damping here. And so let me, so the final equations we're working with, I'll just write it here without deriving it. So this, we got an equation of the form mu L and GL the same thing here. Okay. So here this is as promised, the mu L is damped by these powers starting from the value at the end. So that's saying that you fix the physical mass of the particle, the bare mass is has to be fine-tuned, but all your values of mu L are damped compared to that. So this here there's the propagation, the effect of the mu L doesn't last very long. Here the effect of the W naught, which is the initial value of W naught, does not last very long because of this. But here it lasts. And because of that, what you do is instead of starting from G naught, you start from some GL naught, which is near L. Okay? And then we solved this iteratively, and we got a recursion relation for GL plus 1 in terms of some function Vg of, we call it some notation. So this means that the step size is 1. And from this, recursion relation which relates GL plus 1 to GL, we got a beta function, continuum beta function by a Taylor expansion. So we got a non-trivial beta function. So beta G, which is dGL by dL, was some starting with C GL squared plus something GL cubed. Okay, so this is a so the moral of all this discussion was that the way to deal with this problem, the fact that GL does not get damped, is to, instead of starting from G naught, which is what we did for the other ones, you start from a nearby value of L, calculate a beta function, which can be done, and then integrate the beta function to get GL for all L. And when you do that integral, you get a solution which is something like this. So you get an equation this, and then you integrate it, you get GL is some G naught by 1 minus CL G naught. To lowest order you get something like that. Okay. So here we are able to relate GL to G naught, but not using these recursion relations, but by getting the recursion relation for a small difference and then integrating that. And of course when you expand this, you get 1 plus C L G naught plus C squared L squared G naught squared and so on. And these are the famous factors of log L, the log divergences. So these are the log divergences. This is the log divergences that you get in perturbative divergences that you get in perturbation theory. Okay? So the beta function gives you a way to deal with that. So this is a summary of what we did last time. And actually later on, when in the next class when I talk about Polchinski's argument for the renormalizability, it will be something similar to this. Okay, so just keep that in mind. Okay, so any questions about this? So what I want to do today is a simple analysis of what you do in actual perturbative calculations, the idea of renormalization, and I want to relate it to this discussion because there the log divergences disappear in some miraculous way, and it's not obvious that they should a priori. So let's, just as a toy example, let's pretend that you've done a calculation for G lambda. So you have some coupling constant which you call G bare, which is defined at the cutoff scale, and then what do? You calculate some scattering amplitude and extract a coupling constant at some value of p squared. So you do some calculation like this, and you choose some value of p, typically with some value, and you evaluate the 4-point function at that point and get the coupling constant at that scale. And you get some equation typically which starts off like this: G naught plus some B1 G naught squared log lambda naught by lambda. Of course, this could have higher powers, so I'm just writing plus G naught cubed and so on, plus B2 G naught cubed plus higher log squared. So this is typically going to come from a 2-loop diagram. You'll get log squared because there'll be 2 loops, both of which diverge. So you're going to get terms like this and higher order. So this is typically the structure that you get in perturbation theory. And the question is, what do you normally do to renormalize? So you say, so G naught is your bare coupling. And then to get rid of these logs, what you do is you define a renormalize G naught in terms of a G renormalized plus some factors of log, such that if you plug this into that, all the logs go away. Okay, so what you do is you write something like this: GR. To lowest order, they'll be equal always, plus some A1 GR squared log lambda naught by lambda plus A2 okay. So there are many methods of doing the renormalization. I'm just picking a typical way of doing it, where you write G naught in terms of GR, then you put this into that and hope that all the lambda naught, log lambda naughts have to go away. Log lambda naught is a thing, this lambda naught is a thing that's diverging. So this lambda naught, remember, is going to infinity. That is the so-called continuum limit. Okay, so you just substitute this into that. What will you get? So I'll just write out the first few terms. So you'll get G lambda is GR plus A1 GR squared log lambda naught. Oh, sorry, I should write, what you should do is introduce a renormalization scale, mu. I forgot all about that. So you define a GR and some scale. The scale is put in for dimensional reasons. Okay, you say that some mu like this, and that defines a GR. So this is a definition of your GR if you want, and then you plug it in here. So what do you get? So you get log lambda naught by mu plus A2 GR cubed log squared lambda naught by mu plus, I'll just write out the next term. So this is same thing. I'll just write out this one plus the log square I'll write that also because I want to mu log squared lambda naught by mu squared times wait, I forgot something. This is multiplied by log lambda naught by lambda, and this is multiplied by log squared. So that's what you do, and then you have higher order terms. Oh, yeah. So this is log, and then there's a log cubed. This thing cubed times log squared. Right? That's B2. Good. So this is B1 times G naught squared, which is all this, and then B2 times G naught cubed, which is all that. Okay. Okay, so now what you have to do is to choose these A1 and A2, those are your free parameters, to make sure that the log lambda naught cancels. So of course, so you do it order, and everything is done order by order in perturbation theory. So first of all, of course, you get this relation. To leading order, you just get that. There's nothing to fix. When you go to next order, you get a relation that says this plus what? B1 times GR squared times this. First, next term is order lambda is this one. So there's a log lambda naught from here, log lambda naught from there. Okay, so what do you get? So you get to order next order, you get A1 GR squared log lambda naught by mu plus B1 GR squared log lambda naught by lambda. That's what you get to order GR squared. Okay. So then you say I want the log lambda naught terms to cancel because it has to be finite. So you choose A1 equals minus B1. So choose A1 equals minus B1. That's your renormalization prescription, and then this becomes this whole thing becomes B1 or minus B1 times GR squared log lambda by mu. The log lambda naughts cancel. So this to this order you get G of lambda equals GR plus B1 GR squared log mu by lambda. So to this order you cancel the log lambda naught. So let's just do one more order because that's where you see some constraints emerging. So let's do order GR cubed. So now I'm worried about the log squared terms. Okay. So what are the terms you have? So you have at order GR cube you have A2 plus 2A1 B1 GR cubed log lambda naught by mu log lambda naught by lambda plus B2 . So you have all these terms.
Here, instead of having that lambda posted, we are getting in terms of mu.
Yeah, mu. So mu is supposed to be a finite number. It's a renormalization scale. Okay, that's what you usually do in perturbation theory. Your infinite lambda naught is replaced by a finite mu, and then there's some relation between G naught and Gr that you have to figure out. So remember that when you have things like this is, you can think of this as log lambda naught minus log mu. So let's collect all the powers of log lambda naught. So the coefficient of log, by the way, A1 is fixed to be, we've already fixed A1, so this is actually minus 2 B1 squared, because A1 is just minus B1. So now you look at the GR is the expansion parameter. Yeah. Yeah.
You have B1 G naught square plus G naught cube.
So I mean, everything is in infinite order. I'm just doing it to leading order in.
I'm saying at this order, you have got a term which is simple log lambda naught by lambda.
Yes, from here. No, so this is an infinite series. So I'm just keeping the leading lowest order term. So your beta function, your leading term in this itself will be a complicated power series. This itself will actually be an infinite series. So it won't be just B1 GR squared log lambda. It will be B1 GR squared plus GR cubed and so on. Everything is an infinite series.
When you say other GR square, you don't mean.
No, only in this toy model I'm just keeping, I'm assuming, let's assume that you just got these two terms. Yeah, right. Yeah, so all this has to be done to all orders, but yeah. But I want to illustrate one point. So A1 is minus B1. So this is, so let's look at the coefficient of log squared. So you get A2 minus 2B1 squared plus B2 times log squared lambda naught. And then if you look at the coefficient of log, there's also log lambda naught here. And the coefficient of log lambda naught is minus 2A2 log mu log lambda naught plus 2B1 squared log lambda naught log mu. That's the same thing. Again the same thing, 2B1 squared log lambda naught log lambda, and then minus 2B2 log lambda naught. So these are all the terms that you get if you collect the log lambda naughts. Well, so you have to set everything to 0. So first of all, if you want to cancel this, you immediately get that A2 should be equal to B1 squared. So your second parameter is fixed. That gets rid of this. But now you have a problem. This is not going to cancel. Okay? So if you expect the theory is renormalizable, this has to cancel. So you should find that B2 equals B1 squared. This is a constraint. The theory has to satisfy that. Because B2 is something you calculated. You only have two parameters to play with. You've used them up. So it must be true that B2 equals B1 squared. Okay, and then if B2 equals B1 squared and A2 equals B1 squared, you can plug it in here and you'll find that this also cancels. Log squared terms cancel. In fact, you can see that the whole thing, this whole expression, if you accept this constraint, so if you do your calculation correctly, you should find this is true. And then you can fix this, and then you'll find that this whole thing sums up to GR cubed B1 squared times log lambda naught by mu minus log lambda naught by lambda, the whole squared. So manifestly it just cancels, and this just becomes GR cubed B1 squared log squared mu by lambda. Squared, so it doesn't matter. Right? So it manifestly is finite. But the crucial point I want to make here is that there is a constraint that your series has to satisfy. Otherwise, you would not have this. Okay? So this is something that it's not clear why it should happen, but it'll become clear if you think in terms of the beta function. So anyway, let's write down the final answer. Sorry? Yeah, so every order you'll get constraints like this. Yeah, all these terms will be there, and then you'll have. So if you want the log squared terms to cancel, it's not automatic. I mean, it has to renormalize. Yeah, so that's what you've shown. But if you go to higher orders, you will find that they automatically cancel. That's the point I want to make. Yeah, so well, to be very precise, the coefficients of the log squared divergence have to be consistent with the coefficient of the log divergence. There's some relation, yeah. No, so when you calculate, you'll automatically find that there are these relations. And the fact that this is true, you can easily see. In a minute, I'll show you. Yeah. Yes. Yeah. Yes. Right. Yeah. So you'll get a B3. You'll get a B3. You'll probably find that B3 has to be equal to B1 cubed. Yeah. No further constraints. But I'll show you in a minute that it's sort of automatic. It has to come out that way. Okay, so let's just calculate the final answer. So your final answer is G naught is GR plus B1 GR squared log mu by lambda naught plus B1 squared GR cubed log squared mu by lambda naught. So that's the renormalization relation, and then if you calculate G lambda, you'll finally, with this relation that we just got, is GR plus B1 GR squared log mu by lambda plus B1 squared GR cubed log squared mu by lambda. You see the similarity. Obviously there's a structure in it, right? It's the same thing. So let's calculate the beta function. And so I will erase this. And you'll see the same. Yes. Yes. So that's what I'm going to come to. So let's calculate the beta function. So this is the point, that crucial point. You should think in terms of the beta function. That's what Wilson showed us, that you should try to get that recursion between GL plus 1 and GL. And that has this property. So let's calculate the beta function. So let me write down the original. So let me just leave this for the moment as A2, although we know that A2 is minus B1 squared, and let's just see what happens if it's not. So by that calculation, we have fixed A2. Okay, A2 is minus, but I'm just seeing, let's suppose we have A2 as just a number there, and let's see what it implies. Okay, so what do you do for a beta function? You say that the left-hand side is a bare coupling, it should not depend on mu. So you write dg naught by d log mu equals 0, and then that implies a relation for gr versus log mu. So what do you get? So this is dgr, so I've written dgr by d log mu. So you can write this as d mu d by d mu also, it's up to you, minus, plus b1 gr squared, that's when you differentiate that. But then you differentiate this and you get minus b1 times 2gr times dgr by d log mu times this, And then you do the same thing here. So you get 2a2 gr cubed log mu by lambda naught. That comes from differentiating. It's, have I got my sign right? Log lambda naught by log mu. Wait, I have to check the sign. Plus 3a2 gr squared, etc. Higher order terms, right? So dgr by d, yeah, it doesn't matter because it's, yes, you flipped mu and lambda, so it's right. Okay, so now what we do, we solve for this. That's the beta function. So let's solve for that, and this thing is here, but this is higher order, so I will neglect this. So you'll write dgr by d log mu is minus b1 gr squared plus 2a2 gr cubed log lambda naught by mu by 1 minus b1 times 2 gr. So that's what you get for the beta function. Okay? But this is wrong. Because why is it wrong? If you remember when we did the recursion relations, we got a relation between GL was something like VG L minus L naught GL naught. We did that expansion recursion, and we took the limit that the capital L goes to infinity, and we took the lower limit 0 to minus infinity, and mu L was set to 0, W naught, and we got a translational invariant system of equations. There is no dependence here on L naught. It's only L minus L naught. Okay? Conversely, if you write GL plus 1 in terms of GL, L will not occur in your equation. The beta function equation in that limit, what is that limit? The limit where you set your relevant and irrelevant couplings to 0, and you stretch your scale, in other words, if you imagine taking your ultraviolet cutoff to infinity and you're far away from the ultraviolet cutoff, then your beta function has its translation invariance. GL, the equation for GL has a translation invariance, which translates to a statement that the beta function cannot depend, is a function of, a beta function of, let's say GL, depends on GL but not on L. Okay? So the slope depends on the value of the coupling at that point. It doesn't depend on L because there's no reference point. Your lambda naught is taken to infinity, so it cannot. So you cannot have a term like this. Okay? At least if you take, when you're taking the limit lambda naught to infinity, you're not supposed to have terms like this in your beta function. So what is the resolution of that? The point is that the coefficients of this log have to separately cancel. The coefficients with the log and the coefficients without the log have to separately cancel. Okay? In other words, the coefficient with the log, without the log is this. These are the two terms that have no logs in them. These are the terms that have the logs in them. They have to separate. Huh? Yeah, because if you remember, we got a recursion relation like this. So this depends only on L minus L naught. So it's G L naught and L minus L naught. So if you take L to be L naught plus 1, this is just 1. So the parameter L doesn't occur in your recursion relation. So when you differentiate, there cannot be any L in your beta function. It can only depend on a G. This is in the case where all your relevant and all the dimensionful things have been set to 0. You only have a marginal coupling, and you've taken your cutoff to infinity. So you've done an infinite number of recursions from your starting. So see, it's like, you know, if you have a box and you have a translationally invariant system, okay, when you solve the equation, it still retains some memory of the boundary conditions. Okay, if you calculate some correlation or something. But once you let the box to infinity, the correlation will become translationally invariant. That's what's happened here. So if you're near the initial value of lambda naught, your beta function will have some memory of your starting point. But once you've done sufficient number of blockings, you're far away, there is no memory of your starting. And then everything is translation invariant. So in that limit, what you have to do, so if you're working in that limit, what you have to do is to set this to 0 and then this to 0 separately. So this gives you an equation that says beta gr, which is equal to minus b1 gr squared. And if you want to set this to 0, you see again the constraint that a2 is b1 squared. We had that constraint. When a2 is b1 squared, this will automatically give you the same beta function. If you calculate the coefficient of log, the ratio of this to that is exactly that. You can check, right? So a2 is b1 squared, there's a factor of 2, so there's a net b1 here, and this is related to this gr squared. So the coefficient of dg by d log mu will be again, will have to satisfy. So this condition will automatically kill this term, provided again a2 has that value of b1 squared. So so again the model is, if you do your calculations correctly, this equation came from looking at the log term. The log term will give you the beta function. The log squared terms then will automatically give you the same beta function. You don't have to include that. You shouldn't include that in your beta function. They all give you the same beta function. Okay? And then of course you'll get the solution that we wrote down. If you write down the solution to this, you will get, so what will you get? You will get gr mu2. This is the usual same equation that I wrote down before, by 1 minus b1 gr mu1 log mu1 by mu2. And if you expand this, you will get gr mu1 plus b1 gr squared log mu1 by mu2 plus b1 squared gr cubed log squared mu1 by mu2, and so on. Okay. So here you see the structure that I was telling you, that the coefficient of the log squared and the log are simply related. So in this approximation where I've neglected the beta function is just quadratic, you see the structure very clearly. So when you calculate beta function, you just look at the coefficient of the log term. Automatically, the other terms will be satisfied, and the setting the lambda naught goes to infinity means if you have any power corrections, they shouldn't be there. They all disappear because both the relevant and irrelevant couplings have been set to 0 effectively, and lambda naught has been taken to infinity, so you will not get any divergent powers of lambda naught. Inverse powers of lambda naught anyway will go to 0. So everything is an expansion in log and dimensionless coupling, and if you satisfy the beta function, you get it from the leading log term, the rest are automatically satisfied.
Sorry, can you give a comment about how the powers are actually?
Yeah, so this limit involved taking capital L to infinity, W naught to 0. So remember the W naughts contribute powers of things like 2 to the power of L. 2 to the power of L is like powers of lambda naught, but typically there will be inverse powers of lambda naught. So in the limit lambda naught goes to infinity, those things will go away. So in other words, you will get, if you keep finite lambda naught, you have some memory of that endpoint, powers of lambda naught. But if you let lambda naught goes to 0, I mean infinity, all those terms drop out. Okay? So this argument depends crucially on the fact that you're working with a marginal, exactly marginal coupling. Exactly in the sense, to leading order, it's marginal, and there are no dimensionful terms in your expansion. If you have dimensionful parameters, you could in principle get log mu. So if you have a mass, you could get log mu by m. So that's effectively like having 2 coupling constants. Okay? So if you assume purely dimensionless theory, which is without any masses, this simple relation has to hold, namely that the beta function cannot depend on mu. Okay? In fact, to put it more generally, so you're saying if I calculate g, if I think of t as remember I was introducing a time, so lambda naught e to the power of minus t is my lambda, that's the Rg time. So you can calculate g at tau. If you move a step tau from t, you expect to get some power series. So the point is this has to be of the form g tau plus t. That's what the statement of translational invariant means. So g of tau and t has to be of this type. So if you start from gt and move a step tau, that's equivalent to starting at g0 and moving a step t plus tau because of the translational invariance of your equations. So this has to be of this type, and then you can write down a power series like this. And the claim is that this is your beta function. The leading log term gives you the beta function. Okay? So beta function is only a function of g of t. It's just this coefficient. And if you now calculate g double prime t, it will be just, this will be just d by dt of this one. It has to be. Okay, and this is just d beta by dg times dg by dt. So this is just beta times d beta by dg. So the second derivative, this term is fixed by the beta function.
This is the limit where we take lambda.
Lambda naught is taken to infinity, or your bare cutoff, that is, or a naught is taken to 0. Yeah. So in that limit, this has to hold. Okay? So all these coefficients, these are the log terms, these are the log squared terms, and so on. So the calculation that we said that that this constraint, which a priori was not obvious, except that it was required, is actually coming from this fact that the beta function has to depend only on g, not on the time. Okay. So what's the summary of all this? The summary is, if you do perturbation theory for marginal coupling, the beta function is decided by the coefficient of the logs, then the log squared terms automatically take care of themselves. If you do dimensional regularization, you may have read that you can write an expansion in the pole, 1 over epsilon squared, and so on. The 1 over epsilon term gives you the beta function. And all the 1 over epsilon squared, 1 over epsilon cubed terms, you get recursion relations that they have to satisfy. They're automatically satisfied. So the Feynman diagrams that you calculate have to satisfy those conditions. Even without, I mean, you can make that statement without actually doing the calculation. If the theory is renormalizable, it has to do that. Huh? It starts at 2 loops, yes. Yeah, so everything is, so as I said, I've neglected every term has corrections to all orders. But I'm just taking this leading term and just to illustrate. But these statements have to be true. So this statement is a completely general statement. This has to be true. So the tau squared term is fixed by the tau term. It's exactly marginal, yeah. No, by exactly marginal I mean it's the canonical dimension or engineering dimension 0. The corrections due to interactions. So in other words, you're starting with a recursion that starts like this. Plus order, this is the fact that it's 1 there. That's what I mean by marginal.
So if I want to take a given theory is normal,
Yeah.
how long do I have to work? Perturbating theory normal.
So this structure, so if, actually, so in fact we'll see that when I talk about renormalization 5.4. The crucial point is that the naive dimensions should not get overwhelmed by the anomalous dimension. As long as the naive dimensions are not changed, this argument will go through. Namely, if you have a W which is falling by powers of 4, it will continue to fall. It will not become marginal. In perturbation theory, if you assume that, then this structure will hold. So the crucial point is that the naive dimension should not, of the irrelevant couplings, should not get overwhelmed by the quantum corrections to make them marginal.
So the textbooks we read about, you just count the powers of dimension.
Yeah, that's basically the statement.
Analysis and say anything beyond
Yes.
4
Right.
is not normalized.
Yes.
So that conclusion can be made from this analysis.
Yes. Yes. So yeah. So in fact, right. So the naive. So well, we'll do that in a little more detail next time. So the basic statement is this structure will hold as long as the structure that we started out with holds, namely that the irrelevant parameters are damped by these powers of 2 to the power of whatever dimension, and those if the dimension gets overwhelmed by the canonical, by the quantum corrections, then the structure is modified. Okay. So in perturbation theory, if you assume that that structure I wrote down, recursion relation, that structure holds, then this will hold. Okay. So I'll talk a little more about that tomorrow on Thursday. So what I want to do today is to now switch gear and talk about the exact RG. Okay. So this is all about, well, when we started doing the lattice, in some sense it was we did a blocking, integrated out schemes and wrote down recursion relation. If you had kept all the terms, that would be pretty much exact. So starting from that analysis, we got to all this. The only difference now is we're going to do that in a continuous way, not blocking by a factor of 2, but in a differential way, and then write down an exact RG. So let me go to that, and then last class, tomorrow, Thursday, I'll just talk about the, well, how much time is there? Okay, so I'll finish, well, at least let me get started on this. So I'll just talk about how renormalizability follows. So now I'm going to talk about doing the recursion relation, but in a continuous way, and that is usually given the name So the exact RGA, again, there are many discussions of this, including in Wilson and Kogut's original paper. But I'll do a slightly different description. I think this description is conceptually simpler based on what we've done so far. So the idea is simply to do an integration of higher frequency modes, which is what we've been doing, but get a differential equation where you change the cutoff. Instead of going from lambda to lambda by 2, you just change lambda to lambda minus d lambda. And instead of getting a difference equation, you get a differential equation. So let's start. What's the starting point? You have a Baire theory whose partition function is this. So now I'm using standard 5-4 field theory notation. So we have something like this. Now phi, this is a kinetic term. It's basically 1 over the propagator. So delta you can think of as a propagator. So in momentum, so let's say you're doing it in momentum space, and this delta is just 1 over p squared. Okay. So this is phi box phi. And then there's some interaction piece. I for interaction, B for Baire. So this is your Baire theory. Of course, now you can ask, what is the range of P? And you should actually restrict it to some cutoff lambda naught, your Baire cutoff, and then take the limit lambda naught goes to infinity. We will assume you can always do that. So we're assuming that formally there is some continuum limit that you can take. But that's not important for the discussion. So if you want, you can keep a lambda naught. And the way we're going to keep a lambda naught, instead of restricting the range of P, we'll assume P always goes to infinity. We'll restrict your kinetic term. So we'll write something like this. So we'll choose for delta. So instead of choosing 1 over p squared, you can choose the following. You can cut it off by some function where we'll say that this function goes to 0 when p squared is much bigger than lambda naught. Okay. So what does that mean? That means momenta much higher than this cutoff don't propagate. Their propagator is 0. So this is a smooth way of doing, instead of just cutting off your modes at lambda, which is hard to deal when you do differentiation, it's better to put a smooth cutoff like this. So this could be a function of this type. Example, you can choose any function you like as long as it's smooth. Could be something like this. Falls off like a Gaussian for p squared much larger than lambda naught squared. Example. So now we have this structure. Of course, if you take lambda naught to infinity, it is just 1. Okay. Now what we have to do is to integrate out high momentum modes. And we'll do it in the following way. We'll write phi. So I'm going to write down an equation which I will prove that is true. So I'll write down phi equals, this is just some phi L plus phi H, where L stands for low, H for high. And I'll write delta is delta L plus delta H. Again, L stands for low and H for high. So what's an example of delta L? So delta L could be something like this, k of p squared by, this should be lambda naught squared, p squared by lambda squared. So this lambda is much less than that lambda naught. So this could be the same function for simplicity. So this falls off when p is greater than lambda. Okay. And delta H then is just delta minus delta L. So delta H is delta minus delta L, which is then k of p squared by lambda naught squared minus k of p squared by lambda squared by p squared. So what does this do? This is 0 when p squared is much greater than lambda naught squared. Okay, because both of them are 0. When p squared is much less than lambda squared, both of them are 1. So that's 0. So this is non-zero only in the range lambda to lambda naught. So it propagates modes between lambda and lambda naught. So we have some kind of a scale here. This is 0. This is lambda. That's lambda naught. We want to integrate out, roughly speaking, these guys. Okay? But instead of putting a sharp cutoff, we're putting a smooth cutoff. So we're putting a function kp lambda naught, which will ensure that your bare theory has a cutoff lambda naught, which you can take to infinity. And this here we put a function t lambda squared, which with this lambda, so that the low energy modes propagate with that propagator, and these guys don't. And the delta H is basically the propagator for these guys. Okay? The only point of doing it this way is that you don't have sharp cutoffs in momentum space. Everything is smooth. Now I'm going to write down a statement, and I'll prove it in a minute. So I'll say that ZB intuitively so I should specify the P here, and this is P, just like that. Okay? So this is half phi L 1 over delta L phi L plus half phi H 1 over delta H phi H plus, so this is all inside this, plus S I B phi L plus phi H. So the claim is that this can be written like this. Okay? So I am going to prove that for you. Intuitively it's very clear. So imagine you have a sharp cutoff, then it's very clear. If you have a sharp cutoff, this guy you can divide it into two modes. These are the low energy modes, these are high energy modes. The low energy modes propagate clearly with this propagator, high energy modes propagate with that propagator. So we are saying all your lines of phi are either phi L or phi H. If they are phi L, they propagate with this. If they are phi H, they propagate with that. So that's all this is intuitively saying in Feynman diagrams. But because it's not a smooth cutoff, you have to show this. Okay?
What you were saying, you want to integrate out that portion, that lambda to lambda.
Yeah, so I'm writing it like this, and then what I'm going to do now is to do this integral. I'm going to integrate, I'm going to do that integral. Okay? Yeah. So let me prove this for you. And I think I have time for that, so I'll just. So it's just the following fact that is generally true. So I'll just rewrite this in terms of A and B. General statement that e to the power of minus half 1 by a plus b So I'm just rewriting it in a way that doesn't say anything about high, low, or anything. Just splitting the field into two terms. Okay, this is I'm going to show this. So A and B are just anything. This is not specifically of this form or anything. This is just true. So up to some constant. Okay, so there'll be some overall constant. So let me just show that. So do a change of variables. So we'll write phi 1 plus phi 2 as phi, which is your original phi. So we'll write phi 1 is that, and then we define a variable phi 2, phi prime, which is the following: phi 2 minus b So I change variables from phi 1 and phi 2 to phi and phi prime. Okay. So what I'm going to do is I'm going to start with this expression and go to that. So what is this expression? So this says that phi 1 is a by a plus b times phi minus phi prime, and phi 2 is b by a plus b times phi. Okay. So instead of phi 1 and phi 2, I have phi and phi prime. You can check that the Jacobian matrix is 1, and the determinant is 1. Jacobian, I mean the matrix, the Jacobian is 1. So, well, that's obvious. So you get a by a plus b, b by b plus b, 1 minus 1. It's just 1. Okay. So if you now substitute here this, so you'll get, for phi 1, you just put that, and you can easily see that this will be 1 over a times a by a plus b phi minus phi prime squared plus 1 over b times b by a plus b phi plus phi prime squared. So that is this is equal to that. Okay. So you just expand, you see this is a squared and there's 1 over a, so you'll get a by a plus b squared times phi squared from here. From here you'll get b by a plus b squared times phi squared from here. So that's a phi squared piece from this and this. Then you'll get a phi prime piece which will be phi prime squared times 1 over a plus 1 over b. And the cross terms cancel because the phi prime is multiplied by a, and a cancels, so it's 1 by a plus b, and here also it's 1 by a plus b. So the cross terms cancel, so you've separated it. So this is just a plus b by a plus b squared, so this is just phi squared by a plus b. And this, now the crucial point is that, so this term is this, that this guy is just phi. So your interaction term doesn't depend on phi prime. Okay. So your this integral becomes d phi prime d phi e to the power of minus half phi squared by a plus b minus half phi prime squared 1 over a plus 1 over b plus, so this is all inside the minus s I b phi. So this is all in the exponent. So you can see that the phi prime integral is just a simple Gaussian integral. It doesn't affect anything. You just get some determinant factor, which is a field independent normalization. So you get some normalization times the integral that we wanted to show. So I've been schematic here. When you write integral, it means this. It's all being done in momentum space. Okay. So what have we shown? We've shown that this and this are equal up to some normalization. But we know that normalizations don't matter because we always take ratios of, you always divide by the partition function anyway. So we can do this. So if this is true, if I choose phi 1 is phi L and phi 2 is phi H and this is my A and this is B, then this is true. Okay. So I think we're out of time. So so what I'll do next time is to start with this object and define, well maybe I'll just do that. I'll just define the Wilson action now. Let me do that and stuff. Okay, so the Wilson, so what we're going to do, so we integrate out phi h. So what do you do? So you write ZB is, so let me define this quantity, d phi h e to the power of minus half phi h 1 over delta h phi h minus s I b phi L plus phi h. This I define as e to the power of minus s I, put a lambda. So this is the definition. Okay. So what have we done here? This is the propagator for the high energy fields. The bare action has been split into phi L and phi h. We are integrating out phi h, which is exactly what we did. And the final result of this is some function of phi L. Okay. So this is what is called the Wilson action. So our final partition function is z integral over only the low energy modes, e to the power of minus half phi L lambda.
Sorry, you want the three terms for phi L outside the integral?
Yeah, so there's d phi L, d phi h. No. Okay, so okay, so this part of this is what I'm calling that, right? So that this is I refers to interaction, yeah, and then this comes through. It just comes through without any change. So this is the original kinetic term, and this is that. Of course, this might have pieces that look like that. It's a general expansion, but this is the way it's defined. So this is the interacting part of the Wilson action, and this whole thing can be called the Wilson action. Okay. So the Wilson action is what you get by doing this integral from the, in terms of the integrating out the high energy modes in terms of the low energy modes. So the next thing is to derive a differential equation for this, which is the Polchinski equation. So I'll do that next time, but let me just point out a few things. So in this, what have we done? We've integrated out this fields. So here are the phi h fields, here are the phi L fields, and we've got an action for the phi L fields. Okay. Now you can do more sophisticated things, or not sophisticated, different things. You could introduce a source for this phi h. So I could add to this I could add to this a term plus j phi. Okay? And then do this integral. So do it from here to here. Then I'll get some kind of a generating functional which depends on j, also it depends on phi L. So you'll get some object which, well, so after you've done the phi h integrals, you still have these fields and you have the j. So you'll get some generating function which depends on j and phi L. Right? So what is that a generating function of? It's a generating function of this theory where you integrate out everything, but only up to here. So unlike the usual generating functional where you integrate out everything, this generating function has a lower limit of your integration. So this is like an IR cutoff. It's an infrared cutoff in your integral. So people work with this generating functional, and then you can do further, you can do a Legendre transform and define an effective action, one particular reducible effective action, all obtained by integrating out these guys, not the full thing. Okay? And all these things have a infrared cutoff in them. And then you can write down RG equations for those quantities instead of for the Wilson action. So these are the various variants that people do. Okay? And one of the good things about this is that because you're only integrating out from here to here, there are never any IR divergences. There are no infrared divergences come about because of the zero momentum modes in your theory. They are not being integrated out. So your propagators, see this propagator, if you, so let's just look at this propagator. So this is e to the power of minus p squared by lambda naught squared minus e to the power of minus p squared by lambda squared by p squared. Okay? If you expand this out, when for p is small, the ones cancel, then the p squared term cancels with this p squared. So this is basically p squared by lambda squared minus p squared by lambda naught squared divided by p squared. That's your next term. So that gets rid of this pole. So your delta h propagator, which is what you're using in your integrals, has no pole at p squared equals 0. So if it has no pole at p squared equals 0, there are no infrared divergences. So what you get here is going to be analytic at p equals 0. So that's the nice thing about the Wilson action and all these actions which have an infrared cutoff. You will recover all the infrared divergences when you take lambda to 0, which is what you want to do in the end. So this is a particular choice, but all these guys have the property that delta H will cancel, the poles will always cancel because it's a high energy propagator. I mean, your propagator should propagate only these modes, roughly speaking. So these modes all have p greater than 0. So they're basically of the form 1 by p squared with p in this range plus some small corrections. But it's never divergent at p equals 0 because only this guy is divergent at p equals 0. Okay? So these guys are all, the Wilson action is always analytic about p equals 0. So what I'm going to do next time is I'm going to use this definition and derive the differential equation satisfied by it. So, and that will basically be the, and then I'll talk about using that equation, how Polchinski argues that the phi-4 theory is renormalizable. There's a simple argument you can make to show that. Okay, so we'll stop here.
So even for the general function, you can just write it as a Taylor series expanded around
Yes.
the argument being 0.
Yes.
And then the first term will be this times derivative at 0.
Yes. Yeah. Yeah. Oh, argument you mean J or P? So this generating functional will be a functional of phi L if I integrate out this and J. So the generating functional is function phi L and J, and then you can do various things with it. If you set phi L to 0, you get the usual generating functional.